So our next speaker is Marco Liscindini. Did I say that right?
Yeah.
More or less. And he's coming from the University of Pavia. So,
okay, thanks. So let me open this. Oh, right, I guess it's, oh yeah, there it goes. And I guess that's it. Okay. Thank you very much for being here. Thank you very much to the organizer for the kind invitation. It's a pleasure being here. So today we are going to talk about engineering non-classical light. So talking about parametric fluorescence, which is an alternative, of course, to quantum dots. Now, the outline of my talk essentially is kind of a story from material to a complex source. Okay, so what I'm going to try to investigate is what integrated photonics can do, not in terms of manipulation of the light that we generate, but really in terms of generation of this non-classical light. Now, I don't have to introduce spontaneous fluid mixing, but I want to do a little bit of an exercise with you that is trying to understand where we start. And we start with materials. One possibility is to start with a material that is silicon. Silicon has a strong nonlinearity, but let's try to understand how strong it is. So we take 1 milliwatt at 1550 nanometer. This corresponds to a flux of 10 to the 16 photons per second. And then we shine a 1 centimeter long silicon piece, and we focus this light on a 10 times 10 micrometer square, which is pretty tight focusing, okay? So we do this in bulk, and what do we get? At most, we get 50 pairs per second, okay? So when you do this calculation, well, you get worried. Okay? And then you think, oh, but silicon has also other problems. For example, TPA. Okay, so maybe I should also try to do this calculation with the low index material, but that is even more scary because we know that nonlinearity goes down. And if we take silica, of course, the chi3 is 2 orders of magnitude smaller. So if we do the calculation, we end up with the same power, same focusing, same length, 18 pairs per hour. Okay, so this is ridiculous, okay? So we have to increase the light-matter interaction, and as a physicist, we know that, there are essentially two options. Either increase the matter or increase the light, okay? So option one is going essentially big. So this is what I call the particle physicist approach, okay? So I need to observe, for example, neutrinos. What do? I take a mine, I fill it with water, and then I get Cherenkov radiation. Very simple. So we need a big crystal. You were laughing at it, but actually this has been done with optical fibers. I take optical fibers, I increase the size of my interaction length of kilometers. I go from centimeters to kilometers. And this has been done by Prem Kumar, and there are similar work on it. So these options have been explored, okay? But of course, we are here because we want to go small, okay? And so if we want to go small, we can use a micro-ring resonator, and the micro-ring resonator is nice for a reason. Well, it can be fabricated, but I'm a theorist. It can be modeled very simply. I mean, you can describe it essentially analytically, and indeed this is what we did, and we end up with this formula, which tells you pretty much how the generation rate scale with the parameter that characterize the ring. And as you can see here, there are a bunch of parameters, but in practice, what you can show is that it scales with the cube of the Q and is inversely proportional to the square of the volume. You can think about this like a sort of a Parcel effect for parametric fluorescence. Obviously, depending on your parametric process, this will change. For example, for SPDC, you can find similar formula, but this will be different, okay? Anyway, so sitting here, there are two important effects that are not evident from this factor, that are the mechanism that leads to this enhancement of the nonlinearity in a ring resonator. One is sitting in the gamma, in the nonlinear parameter of the waveguide, and this is essentially what is related to the transverse field enhancement. And the other one is sitting in the Q, and is the resonant effect, the fact I have a resonator. Now, it's a good exercise. Try to understand how these two effects play when we take different materials. For example, imagine this kind of experiment. I want to use 1 milliwatt at 1550, and I want to generate a megahertz, pairs with a megahertz rate. Okay? Now, this has been done already experimentally. In this work, for example, many years ago already, in a silicon on an insulator platform, so high index contrast platform, and also it has been done in silicon nitride. In silicon nitride, you have that nonlinearity is 20 times smaller than in silicon. Now, if you do your math, you realize that the total enhancement that you get from the bulk is 10 to the 8. So it's 8 orders of magnitude of enhancement of the nonlinear process in this device. But where this is coming from? Well, surprisingly, 6 orders of magnitude comes the transverse confinement. Only 2 comes from the resonance. So for silicon, the resonator, well, it plays a role, but minimal, okay? Now, if you go to silicon nitride, as I said, 20 times smaller nonlinearity, so I need about 2 orders of magnitude of enhancement more. And so I need 10 to the 10, okay? And these are astrophysics numbers, but it can be done. It has been done. And if you look at where it's coming from, it's not exactly the opposite, but almost. Most of the point is sitting in the resonance effect. And of course, because of the low index material, this contribution is smaller, okay? But this is very important because when you choose a material, you have to try to understand this because it will set the Q that you're going to work with and all the constraints in your design and fabrication. Okay, saying that, ring resonator work very well. Here I just put some paper. Many others have been shown during this workshop, and others will follow. Okay, so just to show you that you can do energy time entangle photons from a ring resonator. You can work with path entanglement. Now you can work with frequency bin entanglement. And frequency is a very interesting degree of freedom, especially in integrated circuit, because we can tailor the spectral properties of photons up to a point that is not achievable with bulk optics. Because this is related to the fact that we are confining light on a device that has the same dimension of the wavelength that we are using, okay? So, okay, Christmas is past, but I'm already thinking about the next Christmas and what writing to Santa. And I would like to move from these ring resonators because there are problems with this just simple ring resonator. Some of them have been highlighted already, for example, outcoupling efficiency, scattering losses, tunability, and so on. So if I have to ask Santa a few things about the source, certainly flexibility is number one. Why? Because we have seen already in the talk, we need many different kinds of non-classical state of light, not just one. We can play with dual pump for mixing, single pump for mixing, we need squeezing, we need photon pairs, so many different features. And so it's unlikely that one single device will solve all our problems. The other important point is tunability. This came out in the panel. If I have to put on a circuit many of these sources, it's almost impossible they're going to work without a tuning mechanism. And this is crucial. And it's crucial also to use it in designing this source. And finally, but only at the third point, efficiency. In some cases, I need to boost a little bit more the efficiency. In other cases, not. There are, if I need to generate pairs, 1 megahertz is more than enough. If I generate more pairs, then I will have a spurious problem given by the fact that they generate 4 photons, 6 photons contribution, and so on. So efficiency is not always an issue, but sometimes it is. So let's put it in the list. So it's pretty clear that I cannot work with just this sample, this system, but I have to go towards a more complex and hopefully not more complicated device. Okay, so the problem 0, if you are a theorist, is how do I model the generation of light by parametric fluorescence in a device that is complicated. With a ring, there is a strategy. I build an Hamiltonian for the ring, an Hamiltonian for the channel, an Hamiltonian for the coupling, sum all this term, and then I solve the problem. But if I start to have a bigger source, complex photonic crystal cavity or whatever, it's very difficult to find this to apply this kind of approach, and sometimes it's not even possible. Now, a few years ago, we developed a strategy which allow you to model spontaneous fluor mixing in a system with an arbitrary geometry. In the limit of low efficiency, this works very well. If you want to push this to analyze squeezing, it becomes a little bit problematic, okay? But for pair generation, it works pretty well, and you can really use this approach for an arbitrary geometry, okay? There is no limit in that as long as you can solve Maxwell equations linearly. Okay, so a possible approach towards a more flexible and complex system is, okay, a ring resonator works well, so let's take more ring resonators, and we couple them together, okay? Because it's like, you know, it's a nice atom that works very well, I build a molecule. So I coupled this resonator, and it's very interesting because this idea is very old as heralding a photon by an integrated device, because the work that has been shown yesterday by Cheyenne Mukherjee is actually based on coupled resonators. And this was, as far as I know, the first experiment in which they did heralding from a single photon, from an integrated source based on parametric fluorescence. So these are coupled resonators, and there are many, okay? So you exploit slow light due to the mini bands that you create in this crow, and it worked pretty well. So the same approach has been used also with the more exotic structures. For example, in a photonic crystal, it's very difficult to get a combo of resonances. It's almost impossible, okay? Typically, you might have one single resonance, okay? Now, if I want to generate pair by spontaneous four-way mixing, I need at least 3 resonances to accommodate my field. So a strategy that we end up in Pavia was to couple 3 identical resonators. Then you have a mode splitting. The mode splitting creates your 3 resonances. Then you pump on 2 of them, and you generate, or 1 of them, and generating the other 2. So this has been done. And the benefits here is that a photonic crystal system is also very small. Not only you can get a very high Q, but you get a very small volume. And indeed, with the same Q, you get an improvement in the efficiency of about 2 orders of magnitude. So you need basically 2 orders of magnitude less of power to get more or less the same efficiency. This is related to the fact that Q to the cube divided by square is much better in a photonic crystal system. Now, I'm not saying that in the short term you have to think about photonic crystal system, because this is never going to work with foundry. But in the long term, we have to remember that there is no way to get a better Q over V than in a photonic crystal cavity, at least at the moment. Certainly not in a ring. So if you want to if you want to have a very strong light-matter interaction at the nonlinear level, this is a system that you might want to consider. Not in the short term, maybe 30 years, who knows, okay? In the meantime, we work with rings. We go on with rings. And we use this idea of coupling resonators. And if you want to work with this kind of strategy, there is a person you have to contact that is Milos Popovic. Milos Popovic did a great job in this. Very beautiful work. One is this, in which they use a ring resonator to basically tune single resonances, okay, to obtain equally spaced resonances or to suppress parasitic processes. Another possibility is to start and build molecules, always Milos Popovic work, and these works are very, very nicely written, so I recommend it to you if you're interested in the topic. Now, let's try to understand what all these examples have in common. Of course, they are structure in which resonators are coupled, because I told you before. But there is another thing they have in common. The coupling is linear. So all the resonators here are linearly coupled, okay? And so at the end of the day, you start from building blocks, but then you become, you end up with a big system that works as a one thing, okay? So we ask ourselves this question, okay, is it possible to have nonlinear coupling of linearly uncoupled resonator? I want to keep my resonator linearly uncoupled, and yet I want to do nonlinear interaction. Now, for a physicist, this is a question that is enough to do research, okay? But then, of course, you go to a workshop, and the first question, is that useful? Because if you cannot say that it's useful, it's basically of no interest nowadays. Now, as a physicist, for me, this is enough. But it turns out that we will see that this approach, if you can answer yes to this question, and obviously this is the case, this is also useful. So now I will give you an example, but just an example. This is just a philosophy. So you can indeed build many systems in which the resonator are non-linearly coupled and linearly uncoupled. But let's try at least to demonstrate that this can be done with one case. Okay, you can build two resonators, and you can put them together with a directional coupler. You can choose the length of the directional coupler such that when light circulates in the directional coupler, the effective coupling between resonator 1 and resonator 2 is 0. So light will just circulate in resonator 1, and of course in the directional coupler. This will end up with modes where there is a certain field enhancement, which depends on the losses of your ring and the dimension of your ring. And then you can do, of course, you can start to understand what's happening in resonator 2, and there will be another kind of set of modes, and again, light is forced to stay in resonator 2 because the effective coupling of the directional coupler here has been chosen to be 0, okay? And so you have another set of independent mode, and the nice thing is that in the directional coupler, the field enhancement is exactly the one that you have in the ring, exactly the same. Now, the nice thing is that, or the particular thing, is that even if these two resonances come at the same frequency, you won't observe any splitting because there is no coupling. The linear coupling is 0. However, you have a region in which both modes coexist. So you might wonder if this is the region where no linear coupling takes place. Another interesting feature, because we move to the nonlinear coupling regime, is that if I put an ether, for example, on resonator number 2, I can shift all the comb of resonator number 2, and the resonator number 1 comb stays exactly the same. So I can compensate, okay, for any fabrication imperfection in resonator 2 without being worried that this will affect resonator number 1. This is very important for the job we want to do. Now, let's try to understand if we can indeed use this kind of system to do, for example, dual pump spontaneous forward mixing. This was a process that Stefan highlighted yesterday and described yesterday. The idea is to create photons on the same resonances by playing with two different pumps. Okay, I can adjust the two combs of resonances such that I have this configuration here. Okay, and now we will have spontaneous forward mixing taking place here, where the two pumps exist, but also the modes of resonator 1 exist, only in the directional coupler. Of course, the first question is that since spontaneous forward mixing takes place only in the coupler, do we have the same efficiency? Of course not, because only 1/4 of that resonator is working, okay? Nevertheless, it's not that bad, because the field enhancement, which is the most important thing here, is exactly the same of a single resonator for these modes, and for this resonator for the other mode. So at the end of the day, if you do the math, and this is where we did the math, you realize that the efficiency is reduced only by an order of magnitude, 16 times, with respect to the forward mixing taking place in one of the two resonators. Okay, one order of magnitude is not nuts, of course, but remember that the efficiency scales like Q to the cube, okay? So I need to get a 10 from the cube. So I increase the Q of the cube root of 10, and then I have exactly the same efficiency as before. So it's not crazy, okay? But let's try to see the benefits of this, okay? Because so far we're just paying stuff, okay? Now, first of all, I make you notice that since these two combs are independent, there are no longer parasitic processes I have to worry about, because this pump here cannot generate a photon here and another photon here, because there is no resonance here, okay? So parasitic processes are completely suppressed. And this is very important because it's a big problem in dual pump forward mixing. Second point, this is another big thing. Dispersion engineering is not critical. I don't need to do dispersion engineering. Why? Because I can put the resonances equally spaced whenever I want. So there is no problem of dispersion engineering. The only thing I have to guarantee is that the coherence length of the process, delta k, of course, pi divided by delta k, is longer than the directional coupler length. But this is only a few tenths of micrometer. While when I play this trick of spontaneous forward mixing in a single ring, the coherence length must be larger than Vg times the dwelling time of the photon in the ring. Basically, it has to be larger than the coherence length of the photon I'm generating. So we are talking about centimeters sometimes. So here, basically, I don't really need to get crazy with dispersion engineering. Another important point is that the pump here is automatically suppressed. Up to what? Well, even, theoretically, you can expect reasonably, depends of course on the finesse, but even 60 dB, okay, from here to here. And without any filter. Obviously, this is not enough. We need about 100 dB, 120 dB. But this means that then the requirements on the filter of the source will be much less demanding, okay, than what is now. And finally, this is another interesting thing, is that since I don't need dispersion engineering, and if I have tuning mechanism, I can push my resonances where I want, this device can work at many different pump power levels, because it can work also when cell-phase and cross-phase modulation enter into the game. So for example, this means that I can work in the OPO regime, for example, at different power level, because I can always decide at which pump power I'm going to pump without redesigning the device. I found it very interesting and very powerful. Okay, does it work? Well, we did a preliminary result. We did stimulated forward mixing between these two resonators. We enter in this channel, we actually, and with the pump, we enter in this channel with the signal, and indeed we measure an idler. This is possible only if the two resonators are non-linearly coupled. Otherwise, it's impossible, because these three resonators do not belong to one resonator. The resonances do not belong to one single resonator. Two belongs to this one, and the other belongs to the pump. Okay. Very good. So we moved from one single ring to two coupled ring. We can do even more. In integrated optics, you can imagine that the generation of photons is made exploiting the interference of many different sources, okay? So before the manipulation of the state, I have no time to enter in this, in this topic right now, but for example, here we demonstrate, we propose the generation of JSZ states in an integrated device, and this is just an example, just to point out that we don't have just to shrink what we do in the bulk. We have also, in the case of the generation, we have to take advantage of what miniaturization allow us to do. Okay, yeah, I'm arrive at the end. So take-home messages here, because we're all hungry. Okay, what integrated photonics can do for quantum nonlinear optics and for nonlinear optics in general. So the important point is that we can have a significant enhancement of the process efficiency. We are talking about 10 to the 10, 10 to the 12 times the generation in a bulk system. So this is not important for Chi2 processes, which works very well in bulk systems. But for Chi3 is extremely important if you want to work with Chi3. Another important point is that you can control correlation up to a point that is not reachable with bulk optics. This because it would be too much complicated also, moving all these resonance up and down, having depth-free spectral range and so on. It's just impossible to do, okay? And finally, it offers you the possibility to try new configuration. For example, the one that I showed you before, where nonlinear, the resonators are coupled nonlinearly, but they are still linearly independent. So with this, I am at the end of the talk. I would like to thank a number of people, in particular my PhD student Nicola Bergamasco and Matteo Menotti. Now Matteo Menotti is at Xanadu, Zachary Vernon, with which we collaborate, John Saip at U of T, with which we collaborate, and then Daniele Baioni and Matteo Galli, that are the experimental team leader in Pavia. And with this, I thank you for your attention.
Thank you for a fascinating talk. I was curious about if you could illustrate all the various ways in which that photonic crystal is very difficult to achieve fabrication-wise. Thank you.
Okay, so the problem with photonic crystal, the main problem, in my opinion, is the design first. The design because playing, even the strategy that I presented of linearly coupled resonators is actually very difficult. When you fabricate these devices, it's not really true that you can get identical resonators. And at the end of the day, the splitting is not always sufficient to have 3 equally spaced resonances. So I think that this is a topic that is worth investigating with, for example, genetic algorithm, okay? I found that is extremely interesting because you can reach regimes of field enhancement that are absolutely inaccessible with ring resonator, because you can get with photonic crystal cavities Q of the order of million, but volume that are orders of magnitude smaller than a ring. So clearly this is exciting from the physical point of view. From the engineering point of view, though, we have to acknowledge that at the moment, this cannot be the way to go if I want result in 5 years. This is not possible. But we have also to watch a little bit farther than that, in my opinion.